It's the first one. We'll see what happens. So where were we at when we last met? We were talking about, and this is important. So we were talking about integration in two variables. So let's just remember what it looks like. This looks like something like this. It looks like an integral. And typically we would put two integral signs and then the domain underneath. And then we would write it as some generic function that has two inputs. It has an an X and a Y, and then some sort of area element. So this is sort of what, you know, if I put a circle around this, this is the generic symbol for this operation. You take a function and you restrict it to a certain domain and you say, okay, let's associate some numerical value with it. We call it the integral. It looks like this. And this was a new thing. So what we did is we said, we had this Fubini's theorem. So I don't want to use red for this. So what we have is if f, whoa, what the heck was that? Stupid pen has a button on it. See, this is learning in process. Why is it writing? Is that you doing that? Someone messing with me? Austin, is that you messing around with me?
I gave it up.
You gave it up. I don't know why it's writing right now. I don't understand that. We're having technical difficulties. That's great. Oh my God, now everything's moving around. By the way, one thing I should mention is I'm using the built-in whiteboard. There's other whiteboards I've been playing around with. I might switch to some other software if this doesn't, if we have issues with this. See, it's doing this. I don't know why.
There's like a Microsoft one, isn't there?
What, there is a Microsoft one I've been playing with, and there's an Apple one called Sketchbook that I've been playing with. So here's the important thing, and I'm writing very sloppy. If f is continuous, we had this Fubini's theorem. And what does Fubini tell us? I don't know what's this. I don't know if I hit something on this stupid. Give me a second. When all else fails, you reset. I'm gonna reset this sketchpad. Something's not right with it. See, it's writing. I'm not even touching anything, and it's writing. It shouldn't be doing this. You seeing this?
Mm-hmm.
Yeah, that's.
On the.
What would cause such a fiasco?
COVID-19.
It could. It could. Let's try this again. Yeah, it's like changing. There we go. So if f is continuous, what we do is we get iterated integrals. That's what we called it. And these you could think about as ordinary integrals. And what were those, just to remind you? Uh-oh, what was that noise?
That's my computer. I'm sorry, my mom's.
All right, I don't care. I'm just interested. We were in a meeting on Friday, and there was like 5 of us in it, and there was all kinds of crazy noise happening over and over again. It was very strange.
So you can mute yourself in the
Oh,
bottom.
I know you can. That's right. If you want to sneeze or you want to scream and yell at your cats, or if I should have muted me when I yelled at my kid earlier. But anyhow, Fubini says that this scary thing equals what we could write it one of 2 ways. We could say, I'm not going to go through the details of this again, but if you look in your notes, you'll remember what A and B, these are just intervals, or you could do it the opposite way. So we actually scared you on the midterm. We gave you a couple of these. One was easy, one was not easy, blah, blah, blah. And so, you know, I would kind of encourage, even though I told you you can save this lecture and stuff, it would still probably be useful to write this stuff down. I don't know. I feel like you learn better when you write it down. That could just be my opinion, but.
Does that say dx?
Yes, so the top one says dy dx, and the bottom one says dx dy.
Okay.
That makes sense? It's kind of sloppy. I apologize.
It's just running like into the pictures.
What do you mean?
Because I can see your faces like on the side.
You can move that if you want.
How do I do that?
Yeah, you put your cursor on it and click and move. You can move things around. It'll take a while to get used to it. I'm learning too, to be honest.
It's better at the top. There's a side-by-side mode.
Yeah, if you go there, there's different buttons. You can collapse it. You can actually remove it too.
Cool.
Yeah, so there's all kinds of different things you can do. It's a little, you know, I don't know if you guys do this, but I have 2 monitors running, so it's a little easier for me to spread things out. I know that's not always the case for everybody. All right, so here's the thing that you learned right away is that some of these integrals are difficult, not just algebraic reasons, but because of the fact that we try to integrate something, it's just impossible. So what we want to do is instead of what we call rectangular coordinates, and that's what we've been using. So what do I mean by rectangular coordinates? Well, we mean this. You take some point, it has an X and a Y, and how do we reference this point? We think of it as a distance from the X-axis and a distance from the Y-axis. So this is the sort of the coordinate system you guys have used pretty much your whole life. X's and Y's. So what we want to talk about today is using a different way of measuring distance. So here we have a point in the plane, and this is kind of what's important to remember. What is the domain of integration? We're integrating over, you know, what is our function? Our function takes on 2 points, takes an X and a Y. So basically what we're doing is we're integrating over a point in the plane. And what can happen is sometimes the algebra and the calculus can become much easier if instead of using rectangular coordinates, we try something else. And we brought this to your attention in Calculus 2 at the end. And it's also something you may have seen in a pre-calculus course, trigonometry, depending on who taught it. What we can do is we can use, once again, here we go. Why is this doing this? I think. Oh my God. I hate this pen. Oh, I think that's what I realize what's happening now. There's a button on this pen I can click. And if I click it, it'll write just by hovering over. That might be useful once I learn it. But what we can use instead is we can use what are called polar coordinates. So what are polar coordinates? Well, the idea is instead of having your traditional XY, instead you don't write a vertical axis, you just take a horizontal axis. And by the way, this should be horizontal, it shouldn't be crooked, but such as me trying to draw without a roller. You take your point, and instead of measuring it up and down and left and right, you measure it in the following way. You look at an angle from your horizontal axis. And what you have is you have a distance, which we'll call R, and you have an angle, theta. So over here, your points. So here you have X and Y, and over here you're going to use R and theta. Now, you might say, well, why would we want to do this? Well, think about simple geometric things like, you know, if you ever looked at the aerial footage of like a city like New York, all the roads are, say, it's like a grid, right? You know, if you wanted to get from point A to point B, you have to go down one block and up another block. Or, you know, you may have heard the expression as a crow flies, where what's the distance from point A to point B? Well, depending on how you're getting there, you might not be able to take a straight line. So basically what we're saying is the way I measure a location in rectangular coordinates is I take the distance from the horizontal axis and the distance from the vertical axis. But polar coordinates says, let's take advantage of how symmetry, particularly circles, work, and let's measure angles in distances. So this is actually quite useful because then you get a nice relationship between X and Y. So if I switch colors for a second, and I draw some lines, if I draw this line down and make a right angle, I now have that this distance from here to here is X, and this distance from here to here is Y. Anybody have any questions about that? So we're thinking about taking a point in space, a point, not in space really, a point in the plane, and we want to think about its geometry, its characteristics, not by left and right and up and down, but straight distance from the origin and angle from the horizontal axis. So if I add another page, what you see, and I'm going to draw this picture again just because it's important to see. So if I draw what's happening, I have a point here, and I really have a triangle. And if I switch colors so that we have a better idea of seeing this, what are the dimensions of said triangle? We know this side is X, we know this is Y, this is R, and this is the angle theta. Now, without even using calculus, just going straight to basic trigonometry, you can see a relationship between X and Y. So what you have is this very nice thing. X is equal to R cosine theta. Y is R sine of theta. Don't forget that X squared plus Y squared equals R squared. That's the Pythagorean theorem. And if you want, you can solve also for theta. It takes a little trig, but if you solve for theta, you get that theta is the inverse tangent of Y divided by X. So again, I could have started all of this just by drawing this triangle and labeling it, and you could say, okay, these letters and these equations I wrote make sense. But the intuition from it, or the intuition for it, comes from the crap I was thinking about before, or excuse me, not thinking, babbling about before. I mean, what is the whole purpose of these coordinate systems? Well, we're trying to be able to distinguish where a point in the plane lives. Where is it located? And the best way humans have figured this out so far is to draw a coordinate system and measure the distance from points in the coordinate system, whether it's up and down, left and right, like you've been doing, or it's like this, where you say, okay, what is the distance between my point and the origin? And then what is the angle it makes with the horizontal axis? Does anybody have a question about this? All right. So what the heck does any of this have to do? By the way, we did this at the end of Calc 2 very briefly. And again, you may have seen it somewhere else. Okay, so what does this have to do with integration? So here's where we're at with that. So it turns out that these coordinates can be useful when you're integrating.
Did
Hey,
you get that?
I just
Yeah.
did. It says we've removed it. Oh, that's
was-
great. I love it. Why would I be mad? Is that what
yeah,
it's?
that's weird. Did you use your LaRoche email
I
to
did.
sign up?
But
Or something?
there's been talk, yes, but there's been talks that they were going to remove it. So we'll see.
Okay.
If they don't, then we'll just go back to my other plan, which is just use 2 meeting times. Hey, this is fun, isn't it?
Work, so whatever.
I mean, look, this is the, you got to make the best of a crappy situation. So that's what I'm going to do. But I still have my rock star for you guys. See, I figured I decided to wear a shirt. I have, this is fun.
How do you get Rockstar during the panda like?
Dude, they're on sale on my Giant Eagle. They're five for $5. Can't beat that. All right. So, what does it mean to say it can be useful in integrating? Well, let's take a look at that. Is everybody okay with these slides? Is this working for you? I mean, I don't know. I mean, you're allowed to give me your comment. You're allowed to complain. That's what we're here for. I don't mind.
It's a little weird.
It is weird. Trust me, it's even more difficult, like figuring out. Like I thought, I even thought maybe I'll just type stuff up and talk about slides, but then I don't know. There's something about me writing when I'm doing it that I don't know. I just feel like it's better for me. I don't know if it's better for you, but I feel like if I just give you slides, then you're just not going to pay attention. You're just going to, I just don't feel like that's the good way to learn math, but who am I? Okay. So, so what does this mean? So this means we can express this creature. So what did we have before? We had this double integral with this dA. We can express this in terms, instead of x's and y's, r and theta. Does that make sense? So before, think about this. X and y we're telling us are, think about that. We use dx, we use dy, we say f of x and y. But think about what those variables represent. They represent a point in the plane, particularly how far is it from the horizontal axis and how far is it from the vertical axis. Now, what we want to do is we want to try to represent sort of, by the way, let me finish this thought. We want to represent it in terms of r and theta, and we hope that when we represent it in terms of r and theta, the algebraic expressions that were once complicated are no longer complicated. Complicated. And you only need to go back a few slides to see why. Think about the expression x squared plus y squared. If you write that in terms of polar coordinates, it's no longer 2 variables, it's now 1. It's r squared. That's just the Pythagorean theorem. So there's lots of things that look complicated in x's and y's, but when you move them to r's and thetas, they become simpler. Namely circles, namely anything that's curved. Does that make sense? I don't know. So, okay. So the difficult thing is then how do you do this? So is it not letting me, I hit the wrong button. So how do we do this? So what we got to do is we have to analyze what we call the area element. So what was the area element? That's that thing dA. So if you remember how we constructed this thing, if you take your rectangle, what we did is we said, okay, we have this rectangle and we're going to chop it up. Oh my God, into these little rectangles. This is I should use another app to draw straight lines, but this was my delta x, delta y, which is delta A. So you might have to go back in your notes and think about this. We took our rectangle, our domain. Remember, this whole thing here is D. So let's use another color to remind you. And let's see what green looks like. So
I have a question.
yes.
So we're talking about this integral, well, iterated integral, I guess.
Well, we're not talking about an integrated integral right now. We're talking about the double integral.
So how is that different from the other one that we were just talking about with the dx and dy?
Oh, it's not. No, so if you go back, so here's the way you think about it. Let me go back a slide or two.
Sorry.
No, it's just a good question. It's important because if you don't think about, you want to think about why we're doing what we're doing. So this thing, if we go all the way back to the second slide, the double integral by definition is not iterated. It's only iterated when things are nice, like continuity. Does that make sense? This thing is a complicated definition. If you go back, this thing, everybody see the thing with the red circle around it? We're all on the same page. That is complicated. It's defined by this big, ugly limit. It's really complicated. And how we define this is you take D, and D is some rectangle in the plane. Does that make sense? Take your XY axis, draw a rectangle, call it D. Then you take D and you chop it up into little small rectangles. And then you pick those test points and evaluate them in the F, and then you take a limit. It's a very ugly limiting process. If you go back in your notes from one of our last classes, you'll see that. It's not pretty to define. And then what we say is this thing in the red is really hard to define. Luckily, this guy Fubini many years ago says if F is continuous or F has nice properties, we can write it now. So now look at this page, Emily. Now I'm saying this complicated thing is just two old friends. Does that make sense?
That makes more sense, yeah.
Okay.
So if F is continuous.
Well, it actually is. It doesn't have to be continuous. But for us babies in Calc 3, if F is nice, if it's continuous, yeah. It's not as strict as that. If in real life you would say F is piecewise continuous, that means it can have a couple bad spots, but other than that, it's okay. Now, the thing to pay attention to here is if you look at these expressions on the right, you see a dy dx.
Yeah.
Those things tell us in the order in which we're going to integrate it. The top one says integrate y first, and then x. And then the bottom one says do x first, and then y. Now, that might not seem important to you, but if you look at your exam, particularly the problem I gave you with integrals, there were two of them. In the second one, you had to do that trick where you had to switch the order of integration. We did that in class. It's actually quite difficult, right?
Yeah.
And so what happens is the integration could be impossible, or the algebra can just be insanely difficult when you're using x and y to reference your variables. Does that make sense? So basically what I'm saying is given a particular d and given a particular f, these integrals on the right-hand side could be impossible for you to solve, or they can be extremely difficult. Does that make sense?
Yeah. So you would use the other.
Right, but either one of these could be difficult. We'll give you an example in a second.
Okay.
But what we're saying is if you switch, just if you go from one universe to the next, if you say, okay, I don't want to use x's and y's right now. I don't want to measure left and right and up and down. What I'd rather measure is angles. If I remove the horizontal and the vertical measurements, if I instead describe a point by how far it is from the origin, how far is it, and at what angle, then sometimes the calculations become simpler. Does that make any sense?
Yeah.
And maybe it will, maybe it won't right now until we get to an example. But again, maybe this picture will help. If I go, I think the next page. So if I look at this page, then basically this point right here, this point, its only description is given by how far is it from the vertical and how far is it from the horizontal axis. So think about something like a line. A line has a very simple description in xy. It's y equals mx plus b. But what is a circle description using x's and y's? It's more complicated. It's x squared plus y squared equals r squared, radius squared. So it turns out, if you want to describe a circle in polar coordinates, you just describe it only by its radius. So again, this is something you're going to probably have to play around with on your own, have a come to terms agreement with. And maybe it'll be a little easier to pick up on when we do an example or two. But
Yeah.
a very, yeah, but a very layman's way of thinking about this, guys, is imagine that, think currency. I use this all the time, even in Calc 2. Why did we use integration by substitution? Because sometimes X was hard. If we go to U, it's not hard. So we're switching from one universe to another where the math is easier. That's the idea. So turns out that if sometimes X and Y are hard, if I go to R and theta, things will be easier. And we're going to get to an example in a second. We just have to figure out exactly what this dA means in terms of R and theta.
All right.
Yeah, I know, right? It's a lot. Okay, so we go back to this particular idea. Now, the original thing, the very second page I had, it was in red. In order to compute that, I had to take my rectangle, my domain, and I'd chop it up in little pieces, and I measured their area. And the area of rectangles is easy, so we don't really think anything about it. But now, what if we're not using rectangular coordinates? Rectangular coordinates tell us that we can chop up the plane into vertical and horizontal lines. That's what rectangular coordinates tell us. But that's not what polar coordinates tell us. Polar coordinates play the game slightly differently. Polar coordinates say the following. So in polar, you're going to use circles. So instead of, so if this is your origin right here, and this is sort of your horizontal axis, and then what you're going to have is you're going to have, I'm going to change my color here again, because I can. What you could think of the plane being written as a bunch of concentric circles. That's my email. And these are all, I should have used it better. This is crap. Now let's try this again. We're learning all together now. So this is the idea. So the idea is now, if I want to chop up my region of integration, I'm going to use circles. And so really what I'm saying is, if I want to think about a piece in the plane, I have to, what is the area of this piece? Does that make sense? So before, when we use rectangles, let's go back. When we're using rectangles, we know what the area of a rectangle is. It's length times width. But now we're going to use circles, so it's not the same. Now we have this little wedge-like piece. So if I come over here to the right, what does this thing look like? This thing, if we zoom in a little bit, what does it look like? Oh, I'm on the wrong page. So it's going to look like sort of something like this. Does that make sense? Think about, here's a good way to think about it. Think about taking a pizza and slicing it normally, like you normally slice a round pizza. But then think about, you want to drill the middle out of it or something. Again, we got to have an imagination here. So let's. So you want to know, what are the dimensions of this thing? So let's go to the next page. I'll try to draw slightly more usefully. Wish they had a, what is that? Do they have circles here? They should have. I can't believe they don't have like a, oh yeah, here we go. There we go. Ah, I didn't know I could do this. What a time to be alive. So let's take this circle and let's say, okay, let's take another one. Oh, don't do that. Quit moving. I'm going to figure this out come hell or high water. So let's put let's pretend we have our pizza here and we're going to slice it. So I'm going to take my pizza and I'm going to slice it into, say, 8 pieces. Is everybody cool with this? All right, now let me take, let me draw another, see if I can make this happen without killing myself here. Let's see if I can draw another. This is a bad circle. That is bad. I got an idea. Undo. Let's draw another circle inside of this. See if we can do this. Oh, that's good enough. Hold on, let's do one more. Can't figure out how to make it work the way I want to. I don't want any ellipse, I want a circle. All right, well, we can just get away with 2. So the point is, instead of using X's and Y's, horizontals, ups and downs, left, right, I'm using these, what we want to think of as concentric circles. So let's take this piece right here and let's, no, I don't want a damn circle anymore. So let's ask ourselves, if this is the piece we want to measure, what is the area here? Is everybody with me here? You just thumbs up, you eating? Thumbs up. Emily smiling, Anthony. So what is this little piece? Now imagine, here's the way to think about it. Imagine these circles are very close together. And imagine that we are taking very, very small, like we're taking a microscope and we're really, really zooming in. So let me see, can I share? Let's see if I can pull something up for you guys. Now, what do you guys see right now? You see anything?
See the whiteboard.
Yeah, okay, still see the whiteboard. Okay, well, good, because I'm going to show you, what do I want to show you? Where did it go? This one. So now you should see a web page. You guys see a web page?
Yes.
An image. Do you see on the right, you see this polar coordinates?
Yes.
This is much better than what I drew, but you get the idea. You see these circles. So what we want to know is, what in the world is the area of one of these circles? Excuse me, one of these little pieces of the pizza. Right, so if I look up here, do you see my mouse pointing here, everybody?
Mm-hmm.
So here's my piece of pizza, say right here, this big triangular sector. I might want to know, what is just the area of this piece right here? Or what is the area of this piece? Clearly, our eyes don't deceive us. This piece down here is not as big as this piece. And the question is, what are the geometric, properties of these wedges? How do we handle them? Is everybody on the same page as I am right now? All right. And I promise we're going to get to some examples, and that's really what's most important. But I do feel like you got to understand where this is coming from. All right, so if I go back to share, I'm going to share. I'm going to go back to the whiteboard. All right, so this is our little piece we want to know the area of. So what we have to do is we have to use our knowledge of circles. So it turns out, whoop. So if I come over here, so if we sort of zoom in, then we get our delta A. That's our rectangular guy. We would expect that this is going to be approximately R times change in R times change in theta. So this is, and I'm going to explain this in detail, but the most important thing you can do, honestly, is you can go home and draw and think about this. So this equation at the bottom, this what's really not an equation, it's sort of an idea that the area of a rectangle is approximately the area of a rectangle times some factor of r. Now you might say, where does this r and this delta r and delta theta come from? And that's a very, very good question. And it comes from things about circles that you may or may not remember. So let me go to the next page and let's ask ourselves why. Well, that's not how you want to do things. I'm learning, kids, I'm learning. So the question would be why? All right, so if you just do, and you might not know this, if you just do a simple internet search and do, for example, area of a sector of a circle. So we've gone over this a few times before. I think I've done this for you, I'm pretty sure. Or if you just use your, what we call deductive reasoning skills, you can easily, I don't want to say easily, you could figure out the formula by taking a circle and dividing it into so many equal pieces. So basically you have the following. Let me get my pen back here. Where did my whiteboard go? If I take my slice of pizza, this is going to look like this. And what I'm interested in is this piece right here. You guys are seeing the whiteboard, I hope. Is everybody seeing it? Yeah. So let's imagine that this is the origin. So maybe we have this, and then this is theta. But let's imagine that we're zooming in, and then what is this distance from here to here? Well, let's call this delta theta, because I'm going from one theta to the next. Just like if you go back to Calc 1 and Calc 2, when we would say we have x1, x2, x3, x4, x5, all those little partitions, and then we would measure the distance between the two. We'd say delta x is x sub 3 minus x sub 2. Do you guys remember those things? Maybe you have to go look. The idea is we can do the same thing with theta. We're chopping our circle into like not 360, I know, say we're going to take, we know a whole circle is 360 degrees. Let's chop it into 1,000,000 pieces, 10 million pieces. And let's call one of those little increments delta x, or excuse me, delta theta. Okay, and then what would be this distance between here and here? Well, or this distance between here and here? Well, we can think of this as being delta r, the change from one radius to the next. So let me be even more descriptive. Let's suppose this is theta sub I, and let's suppose this angle is theta sub I plus 1. So again, I'm sort of hoping that you go back to thinking about how we did integration even in Calc 1. You chop the domain into n equal pieces. You know, I would take I take the interval from A to B and chop it into n pieces. Well, now I'm not using x's and y's. So I'm not defining a function on an interval. I'm defining it on r and theta. So I'm going to take the theta and I'm going to divide it into pieces, maybe 5, maybe 100. Let's call the first one at theta 1, theta 2, theta 3, theta 4 as we go up. And let's measure. Again, we're zooming in on a small piece, but I'm drawing it in large so we can see. This is, you know, I'm pointing at the board like you can see it. This is, but if you could see my cursor here, we're imagining that these two angles are close together. And then these two radiuses are close together. So what do I mean by this? This could be radius I, and this would be the next guy, which would be radius I plus 1. So the idea is that when things are very, very small, this little curved region actually looks like a rectangle. Now we know it's not a rectangle, but if we use some basic ideas from what you probably would have learned a long time ago, and clearly you forget because most people have to look it up. I look it up every semester myself. What is the area of a sector? Well, the area of a sector is the angle divided by 2 times the radius squared. So let me draw that. So in general, if I have this piece of a circle, if I have my slice of pizza, the area here is, so let me see if I can get this to look pretty. It's theta over 2 times the radius squared. That's the area of this slice of pizza. So imagine this is theta, imagine the radius is r. So if I just take a slice of pizza, that's its area. You can go home and do this. Let's sort of put this in a box so that we don't confuse it with what I'm doing, because I'm using these variables in different contexts. So this is my pizza slice. I know it looks bad. It ain't a triangle. But that's a good way to think about this. Imagine if I have a very small piece of my circle, my slice of pizza, it's going to look triangular, right? What's the area of a triangle? 1/2 base times height. So you can use some ideas from that. Okay. Now, if I look at the picture, the big picture on the page, you can imagine I have a slice of pizza, and what I'm trying to do is take a smaller slice out of it and then see what is the area of what's left over. All right, so let me remind you again, what's the piece I'm looking at? I'm looking at this piece. So you have a slice of pizza, and you don't want to cut it in half, because then it wouldn't, you know, what you want to do is you want to cut it so that you get this smaller piece at the bottom. So let's look at this. This is just, you know, what time is it? It's 1:30. We're going to have to wrap up soon so you guys can de-stress. So what's the total area? Well, the total area, I'm going to go back to blue. So the total area, what is it? Well, the total area is, you'd have to measure the distance. What's the radius? So the radius, so the total area is going to be delta theta over 2. And then the radius would be r sub I plus 1 squared, because that's the whole slice of pizza. But we don't want the total area. We want the total area minus the smaller piece. Does that make sense? That gives us the little wedge that we want, the area element. Oh no. Okay. So again, we want the piece that has the question mark in it. What I've done down here is given us the whole piece. So I need to subtract out. So let's get a different color. And I need to subtract out this green piece now. So let's make it clear what I'm talking to myself in the third person. Holy hell. So the piece we want equals total minus the smaller piece. So what is that going to be? That's going to be, we already discussed this, it's delta theta over 2 times r sub I plus 1 squared. Now what's the smaller piece? Well, its angle is also delta theta over 2, but its radius is r sub I squared. Now let's do a little bit of algebra. Don't get frightened. One of the things you're going to see if you look at this screen is you see a difference of squares. Remember back in high school you had like, x squared minus y squared is x minus y times x plus y. So let me go over here and let me just give a red box that reminds you of difference of squares. If I have, say, a squared minus b squared, I can always write this as a minus b times a plus b. That's a difference of squares, right? So I want to apply that to the I sub plus 1 squared and the r sub I squared. So if I just get a little creative with my factoring, so if I pull this delta theta out, what's left is an r sub I plus 1 minus r sub I times r sub I plus 1 plus r sub I. Now what is this guy? This is delta. This guy is just delta r. That's the definition. Remember, delta, any variable, is just one guy minus the next guy. And then what's left over is this guy, r sub I plus 1 plus r sub I. There's not much we can do with that. Now, let me ask you a question. Oh my God, what's happening upstairs? We have children sacrificing each other upstairs. Let me ask you a question. If r sub I plus 1 and r sub I are very close together, then what we're saying is that we can make this approximation. Oh my God, what's my kid doing? We can say that this is approximately the following. Delta theta over 2 times delta r times 2r. Now you could call this anything you want. Maybe you call it r sub I. Does that make any sense? So what I'm doing is I'm saying when these two numbers are close to each other, this sum is just it's approximately 2 times one of them. And so what that means is, that means the following. So what this suggests is, that delta A is approximately R times delta R times delta theta. So again, go back. If you go back one page, that's what you see in the bottom right. You have delta theta over 2, but these 2's are going to cancel. So if I take my red marker, that 2 and that 2 cancel, and I'm left with delta theta times delta R times R sub I, or R sub I plus 1. It doesn't matter. Because remember, what is our ultimate goal? We're going to set up a Riemann sum. Now, we're actually not going to do it, but that's what you would do. So let's get to that, because that's where we want to go. I don't want to build all that up because we've done it enough times now, but we did give you some intuition and some motivation to where it's from. So what we end up getting is the following. So this, if we build our Riemann sum correct, gives the following, and this is the big excitement, and then we're done. So what does it give? It gives that our double integral that we are really worried about in the beginning can be rewritten as, we could replace x and y with r and theta. So what is x? X is r cosine theta. Y is r sine of theta. And then instead of doing dx, dy, we have r, dr, d theta. And then now we are integrating over a different region, which I'll call capital R. So, Emily, you might say, oh, Grady, why did you spend an hour, blah, 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 why don't we just do examples? I get that. I understand that. But my point is I don't want to do the rigor of building the Riemann sums. We've done it enough times. But I do feel like it's important that you understand some of the intuition and motivation from where we're coming from. Does anybody have a question? As you're all, microphones are off. You're like MF and me.
Sorry.
I'm
No,
kidding.
no, no, you're good. I have a quick question.
Yes.
So delta R, of course, is the change in the radius, but
Yes.
R is fixed. Is that because it's
Well, remember, okay, so this is good. This is part of the issue that, you know, I'm thinking of it differently than you. Yes, it's fixed. R sub I is fixed. R sub I plus 1 is fixed. But I'm not saying anything about it other than it's a fixed one. It could be R sub 1 and R sub 2. It could be R sub 37 and R sub 38. It doesn't matter. What I did is I am looking at, and it might be useful if you have the book to go read this section, or at least look at the pictures, because they have these nice colored pictures of all that. But really, what's that?
What chapter is it?
This is chapter what, 15? I don't know. I have to look it up. You'll find out next time. I'm going to give you, I'll give you the home. Actually, here, I'll tell you exactly what it is. I have the book right here. It is, well, polar coordinates we did in Calc 2, that's chapter 12. But when you come to integration in polar coordinates, that is chapter 16.
Thank you.
Yep. So I'm going to assign some homework, obviously, and we will definitely show you how to do these. But back to your question, Austin. So what I did is I showed you what the area is for one of those polar regions. But you have to imagine, if you build a Riemann sum, you're going to have n times m of them. Because remember, what we're going to do, we're going to take theta. Theta is going to range. Maybe it ranges from 0 to 2 pi, maybe not. It depends on what my region is. And the only way for you to really get this is when we do examples. And then R is going to range. What's the radius? Well, it depends. Is it from 0 to 1? Is it from 2 to 47? So those things are going to change. So what I did is I said, here's one region. What's its area? Now, if you want to construct the Riemann sums, you would realize that there's going to be, say, n times m of them, just like there was with our rectangles. And then you have to build a double sum for this. It's very tricky. So that's why my thought is to just show you how, really the reason I went through that is because if you look at this integral on the right of your page, notice it's not just d variable. There's this extra r here. This doesn't show up when you're in x's and y's. You don't see x dx dy.
So why do we have that r then?
That's what I was just trying to show you. This extra r comes from us, the curvature in that region.
Oh, from doing like the delta thing we were
Yes.
talking about? Okay,
That's right. So this is that's why I spent a lot of time with it, to try to illustrate that you get three terms, not just a dx and a dy. You get a variable times dr, d theta.
Now that variable, when I'm assuming we're integrating this because that's what it is. Does that get like multiplied, or is that another?
Oh, it's going to depend. So let's do an example real quick. If you guys want to hold on for a few more minutes. Again, if you got to go, you got to go. I won't be mad. Let's do an example. We'll do a very basic example to see how it works.
Where are we going?
What's that?
Where are we going?
I don't know. Maybe you have things you have.
I have to pack up my whole dorm room tonight, so
Oh, are you still there?
Well, I'm at home, but I was assuming I was trying to get approved to stay because of my job, but
Yeah, and they wouldn't let you.
help.
Oh,
And
no,
Allegheny
it's not
County
like
is
they don't
closing.
want you to. It's not like they don't want you to stay. It's the state will really come down on them hard.
Yeah.
Because all it takes is one person to get sick, and then everybody's screwed. I mean, you know, that's why I said people don't pay attention. We should actually we should stop integrals, and we should show you how the basic models that these knuckleheads are using to study these diseases. It's pretty fascinating. I'm going to do that in Calc 2 because we're actually doing differential equations, but that's what they are. So you may have heard these fools on the news talking about the SIR model and all that. That's what it's basic. It's not basic. It's really hard, but the math behind it is not too difficult for you guys. You guys know enough right now to at least see them. Anyhow, let's do an example. So let's integrate. We're going to write it down like legends. Let's do this. Let's say e to the x squared plus y squared, like this. So let's integrate this where
Why are you gonna do this to me?
d is the disk of radius 2, centered at the origin. So what does D look like? Let's go over here. It looks like this. You know what? We have skills for this. We don't need O'Grady.
We learned this, O'Grady.
I know. What in God's name? I'm gonna kick my own ass here. So draw my circle. That's a pretty one. Now I'll get my lines. And again, the radius of this guy is 2. So this right here is D. Now look, describe D using an X's and Y's. So let's go over here and let's do this. What is D? Here's a scary one. So remember how we write it like these adults. We say it's all X and Y such X squared plus Y squared is less than or equal to 2. So that's the set of all points that their distance from the origin is no more than 2. We cool with this? Now, if you go and try to set this integral up using X's and Y's, you're going to run into a pain in the ass. The bounds would be really difficult. Try doing it. So Emily, if you want to realize, if you want a good motivation for why we're doing this, if you want to kill yourself, so try to get the bounds in X and Y. It ain't fun.
Yeah, I'm gonna have to pass on that one.
Well, so what I'm saying is think about it. How if you fix X and ask where Y range is, then you have your bounds. You're going to have this, just to give you a sort of a precursor. You're going to have this. You're going to have -1 to 1, and then down here you're going to have 4 minus x squared with a negative sign in front, and then this one is going to be 4 minus x squared with a positive sign in front. And then this is going to be e to the x squared plus y squared, and then it's dx dy. Actually, I have it backwards. It's going to be I wrote it in dy dx, actually.
I'm literally stressed just looking at that.
Don't be, but that's, well, you should be, actually, because it's a pain in the ass to integrate. So
You said that was 4, not a y.
Yeah, that's a 4. Why,
Okay.
Where does the 4 come from, by the way? The 4 comes from the fact that this is, what's the radius? The radius is 2. What's 2 squared? 4.
Got it.
So where am I getting that 4 minus x squared in the square root? I'm solving the original equation of the circle for y. So what's y? You get y equals 4 minus x squared, right? And then you take square root of both sides, all that stuff. Now, that integral would stink because you integrate first with y and then you have to plug those square roots in. That stinks. So instead, use polar coordinates. So in polar, this is very nice. So let's just draw. Here's how I would encourage you to do it. This becomes e to the r squared, r dr d theta. Now, what are your bounds? So here's what you need to ask yourself. You ask yourself, where does r range? Where does the radius go from? If I look at my region, what is the smallest points are 0 from the origin, and who are the furthest guys away? 2. Now, what about my theta? How does my theta range? Well, I'm doing the whole disk, so theta goes from 0. Oh my God, I did it again. I hit that stupid button. This pen has like buttons on it, which I have not figured out what they do other than cause me a headache right now. Doing it again. I end up killing myself here. This should be, I'll just do it this way, 2 pi. This integral is much easier than the one on the previous page. If you don't believe me, try them both. So what polar does is it takes advantage of the symmetries inherent to circles. And believe it or not, it's not like we're just making things easier for the sake of making them. Oftentimes in the real world, things are circular or curved, and in that case, polar is better at telling us how to measure distances. Now, how does this integral work? Well, let's solve it. So if I can get this to stop doing it. It's not going to, is it? This integral requires a u substitution. So I'm going to unplug this stupid thing again since I somehow managed to mess it up. And it's still doing it. Heavens to Betsy, it's telling us this is a sure sign that class should be over. I don't know why it's doing that. So here we go. So what we need is we need a u sub. Remember that from Calc 2? I'm writing with my mouse right now until I get to the next page. So what is the correct substitution? You need u equals r squared. And what does that mean? That means that du is 2r dr. So the integral theta doesn't change. It's 0 to 2 pi. Now my bounds are going to change for r. They're going to go from 0 to 4. And this becomes e to the u du d theta. So you're going to have to work on that yourself to convince yourself. But the 2r dr is replaced by du. So we're missing one thing, which is out front. We're going to have this extra factor of a half. So what you need to do is convince yourself that the previous page is, in fact, reduces to this integral. Now, the integral in terms of u, this is a relatively simple integral. This just becomes e to the u evaluated from 0. These 4's and u's are going to drive you crazy, Emily. I'm sorry. Let me get my eraser out on this creature. So that's a 4 by that line, but this is a u.
Context, I got it. I got you.
And then I got to plug in 4, and I have to plug in theta, or excuse me, 0. So this becomes 1/2 times this integral. And then when I plug in 4, I get e to the 4 minus 1 d theta. Why am I getting -1? Because when I plug 0 in, e to the 0 is 1. Any questions about this before we finish? Now, the nice thing, another thing you'll notice when you do examples of this, maybe you go to YouTube and watch polar coordinate integrals. Almost all the time, what you end up doing is the integrals are easy because there's no theta and r connected. So notice that I integrated r first, no issues. Now there's no theta. Do you see a theta? No. So this thing actually, when you integrate this, it's just like integrating a constant. So let me explain what oh, it won't let me. I can't do any more pages. What? This is the last page they give us. We have to get cute here. They won't let me add more than 20 pages. Jerks. So what does this become? This becomes e to the 4th minus 1 over 2 times 2 pi, which becomes e to the 4th minus 1 times pi. And that's your answer. So please fill in the details of that. Yeah, don't, I know, but hey, why is it just 2 pi? Well, think of that integral. All you're integrating is a constant. So you integrate a constant, you just get the variable. So it's theta from 0 to 2 pi. So that's why it's 2 pi. And by the way, this happens a lot. Lots of these integrals, there's never a theta that shows up. So it's very, very useful. Not all of them, but in a lot of them. Was this fun? Is your head ready to explode?
A little bit.
All right, so we suffered through it. This is good. We only had to do one. Do you guys have any questions right now?
No.
All right, so I'm going to put, what I would encourage you to do is maybe go to YouTube, watch some polar coordinate integral examples. I'm going to post a homework assignment for you to practice this. On Wednesday, we can answer some questions. I think what might be best for me to do, and if I have time, is maybe for the homeworks now, to save us time, I will just do, since I have all this set up, maybe I'll just write up solutions to the homework and then post them to Canvas. That way you can watch videos that I do. I don't know. Or maybe
Useful.
I know it'll be useful. The problem is how much time is it going to take, you know? If I can do it efficiently, I'll do it.
Okay.
We'll still do examples on Wednesday for sure. And don't forget, if you're on Zoom, I'm going to have office hours virtually. You're more than welcome to join them. Yeah.
When are your, because
I have to figure that out, but what I'll normally do is if you want to join the virtual office hour, instead of me sending a link to everybody because I'll lose my mind, is you just send me an email and then I'll just send you the link to that meeting and then you can ask any questions you want.
Okay.
So I'm still trying. If you can imagine, it's been hell the last week with all the crap we have to do. So I'm trying to give my classes just as much time as I'm giving the department and all the other stuff. I'm trying to, So if there's anything you have questions about or need with the class, don't hesitate to blow up my email. You'll get responded to sooner. But don't worry about any homeworks, turning them in right now and all that. You guys pay attention. We'll get through this. All right. Any other questions?
I had a question about the scheduling. Should I
Oh yeah,
stay on?
you and I. But I just want to make sure before I kick all them off.
Okay.
All right. Well, all right. Then I'll see you guys. And I'm gonna stop recording now. And hopefully, why won't it let me do this? Okay, cool. And then I will see you guys, Wednesday.
Wednesday.
All right,
Yeah, sounds good.
Take care. Be
See you
safe.
later.
Later.